Welcome to we're doing a question from LeetCode called Kth Largest Element in an Array. This is a really fun problem. So what is it asking? Given an integer array nums and an integer k, return the kth largest element in the array. Note that it is the kth largest element in the sorted order, not the kth distinct element. Can you solve it without sorting? So example 1, we have our input nums and k is 2. We want to return the second largest element in our array. That's going to be 5. The largest is 6. The second largest is 5. Example 2, this is our input nums. We want to return the fourth largest element. That is going to be 4. And we see that we have 3 larger elements in our array at the end over here. We also have some constraints. Okay, so how are we going to solve this? And how are we going to solve this without sorting? Well, first, if we did want to use sorting, what would that look like? Well, that would be really trivial, right? All we have to do is just sort our input nums. So we're going to do nums.sort. This is going to sort our input in increasing order. And if we want to return the kth largest element, we're basically counting k from the end. So all we have to do is return nums at index length of nums minus k. Now, if we look at example 1, we have 6 elements in our input. And that one sorted would look like the following. Now, if we want to return the second largest element, all we have to do is length of nums, so 6 minus k, which is 2. We want to return whatever we have at index 4. So 0, 1, 2, 3, 4, right over here, which is 5. So let's go ahead and submit this. And it is accepted. So this is how we would do it with sorting. But we want to do this without sorting. Now, one way to do this is through the use of a heap. What we're going to do is maintain a list, a heap, size k, and just maintain those k elements in sorted order. Every time we come across a new element, we're going to insert that into a heap, sort that size k, and remove that smallest one should we exceed the length of k. And in the end, return the smallest number in that heap. So what would that look like? First, we want our heap, so let's initialize that to be empty, and we just want to loop through all of our numbers. So for num in nums, we are going to just add our number into the heap. So heap q.heap push. We are going to be pushing into the heap with our number. And if we exceed that length of k, so if length of heap is greater than k, we want to remove the smallest element. We always want to keep track of the k largest elements. So if we have more than k elements, we want to remove the smallest one. So heap q.heap pop from our heap. In the end, once we are done looping through all of our numbers, we are going to be left with a heap size k, and we just want to return the smallest element, right? So we're just going to return whatever we have at heap index 0. So say we had example 1, I'm going to change k to be 4 just so we can work with a slightly different example. Going through this line by line just to see how this is going to run super quickly, we initialize heap to be empty. We're going to loop through all of our numbers. So we start off with 3. We are going to push 3 onto this heap. So heap now has 3, but the length of heap is not greater than k. It's not 4. So we're not going to do anything. We're not going to pop. We're just going to go back in the loop. We're now at 2. We push this on. We're still not greater than k. We go back in the loop. We push on 1 to the heap. Go back in this loop. We're going to push on 5. In this loop again, we just add in 6. And now we are greater than the length of k, right? We have 5 as our length, but k was 4. So what we're going to do is pop off from heap. We remove the smallest number, so we're going to get rid of 1. Now we have the k largest elements we have seen up until this point. The k largest elements are 2, 3, 5, and 6. Going back in this loop for the last time, we come across 4, we go ahead and add that in. We are greater than the size of k, so we pop. We get rid of the 2, and now we are done going through this loop. There are no more elements to iterate through, and we're just going to return what we have in heap of 0, which is 3. 3 is the 4th greatest element in our array. And just to sanity check this would have been our array in sorted order. The first largest would be 6, second is 5th, third is 4th, and 4th is 3rd. So we are going to be outputting 3 just like we should. Now, time complexity for this solution, we're not sorting everything, so this is not going to be n log n, but we are maintaining a sorted list size k. So every time we insert an element inside, it's going to take log k to find the position in which it should go to. Now, since we are doing this for every single element, the time complexity for this is going to be n log k. Let's go ahead and submit this, and it is accepted. So we did this through n log n and n log k, but can we do even better? So say we have the following input example. This is our input nums, and we want to find the 6th largest element. So what would that be, right? If we were to sort it, what would that look like? It would look like the following, and the sixth largest element would be 1, 2, 3, 4, 5, 6. What we have at index 3, this would be our kth largest element. So I'm also adding index 3 here, so we know that the sixth largest element would be at index 3 if our array was sorted. But we don't want to sort. So instead, what are we going to do? We're going to pick a random number. Say we pick 4 over here, and we're going to say 4 is our pivot. So I'm going to write this down. Pivot equals 4. We're now going to partition the array around our pivot. All the numbers that are less than our pivot are going to go to the left, and everything greater than it is going to go to the right. Once we finish partitioning our array, this is what it's going to look like. All the numbers that are less than 4 are going to be to the left, and everything to the right of 4 is going to be greater than 4. Which means 4 is already in its sorted position. If we were to sort our entire array, 4 is exactly where it needs to be, because everything greater than 4 is to the right of it, and everything less than it is to its left. So if we wanted to return the fifth largest number, not the sixth largest number, we could have returned 4 right away. We know for sure there are 4 numbers that are greater than 4, which means our fifth largest number is going to be 4 itself. And we don't really care if those numbers that are above us or below us are sorted or not. We're only concerned about that one particular number, right? Alas, we don't want the fifth largest number, we actually want the sixth largest number. So what are we going to do? All we need to do is repeat the same process in this lower half over here. We know for sure we have 4 numbers that are bigger than 4, and we have 4 itself. So we have our 5 largest numbers in our input nums on this right side, which means somewhere in this half will lie our 6th largest number, the kth largest element in our array. So we're going to repeat that same process in now a smaller portion of our input nums. So repeating that same process for this portion of the array, say we pick a random number, say it's our rightmost point again, so we go with our pivot being 1. We're going to partition the array around the pivot again. So this is what our array would look like, right? We don't really need to touch anything over here, so this is going to remain as is. We're not sorting it, we're not messing with it whatsoever. And we have 1 in its sorted position. Everything greater than 1 is going to be to the right of it. Everything less than it is going to be to the left. So we know for sure what we have at index 1, but we wanted to return what we had at index 3, right? The kth largest element is at index 3. So now we know we need to narrow our search again. We're now going to look in this half over here. We're not going to bother with this because we know those are all greater. We're also not going to look at anything that's below us because 1 already was less than k, right? If k was the 6th largest element, 1 would have been the 8th largest. So anything less than us is only going to get further away from that k we want to return, which means we are now going to look within this half over here. So say I pick a random pivot and I go with pivot 3 over here. I only had 2 choices, 3 or 2. What would my array look like now? This is what my array would look like, right? We only had to compare one number basically against the pivot, and that was 2. It was less than our pivot, so it's going to go on the left. Now our pivot is exactly at the k we wanted to return, the index 3. So we're going to go ahead and return that. And notice how we didn't touch any other number or compare any other number that was outside that particular scope of the array we were looking within, right? We only compared this number over here. We didn't bother with anything else. So all we need to do is return this 3 over here. Now, why is this O of n time? Well, the first time we picked a pivot, we compared every number in our array against that pivot. So we made n comparisons in total. Then once we picked our next pivot, we only needed to compare half of our array. We only looked in this half, right? So we made n over 2 comparisons. Then since we still hadn't found our kth index, we made another pivot and partitioned along it. So we basically split our array in half again. So we had to do n over 4 comparisons. If we keep doing this for our input, right? We first make n comparisons, then n over 2, n over 4, n over 8, and so forth. This is something that is called a geometric series, and it converges at 2n. And 2n is basically an order n operation, right? We don't care about constants. But wait a second. What if, since we are picking random pivots, we don't pick pivots that will cut our array in half every single time? Say we had the following input example. This was our input nums, and we wanted to find the kth largest element. So say we're picking a random pivot, and we went ahead and picked 8. If we were to compare all the numbers against 8, they would all be less than 8. So this doesn't help narrow our search down much, right? We just know we need to look somewhere within this half over here. So we basically just made n comparisons. Now say we use 7 as our pivot, everything is again going to be less than 7, so this is going to be our new half that we're going to look in. And then we pick 5, this is going to be our new half. So every single time we're making one less comparison, but we are comparing every single element for all the elements in our input num. So this is actually an n squared operation. And this is not linear. So worst case actually for this approach is n squared. However, this is the worst case, and usually we can assume that we are splitting our array more or less in half, so amortized across all of the pivots and partitions that we run, we can say that this is an O of n linear approach. Now that we know how to do this, let's go ahead and code this up. To code this up, we're actually going to level up just a little bit and make one more minor optimization. Instead of having a partition of all the numbers that are greater than a pivot, less than a pivot, we can actually introduce a third partition, everything that's equal to our pivot, a range for that. So say we had the following example, we wanted to find out our 5th largest element in our array. So whatever we would have had in this index if our array was sorted. Actually, in this case it is, but say we had picked 2 as our pivot initially, and after comparing all the numbers against this 2, everything greater than equal to it would be on the right, everything to the left would be less than it. So now, since the index we're on doesn't equal the index of what we wanted to return, we would now have to search in this half. And we would have to keep doing that, splitting it in half every single time. However, if we had a range for all the numbers equal to our pivot, we wouldn't need to wait until our index equaled k exactly. We can just see if k lies within that range of everything equal to our pivot and just return right away if that was the case. Just return whatever we have at index k. So that's what we're going to do. We're going to introduce a third sort of sorting, everything that's less than our pivot, equal to it, and greater than it. Now to code it up, say we have the following input example, k equals 5, and this is our input nums. The first thing we want to do is redefine what k is, so it's going to be length of nums minus k. The length of this array is 9, so 9 minus 5 is going to be 4. We want k to be 4. We're going to return whatever we have at this index once it's sorted. Now all we want to do is write out our quick select function, so def quick select. We just want bounds for which part of the array to look in. So we're going to have left and right. We know we want to sort our array into thirds, everything less than a pivot, equal to it, and greater than it. And we want to do this in place. So how are we going to do this? Third video I ever made on this channel was about this problem, this situation, sorting in place into thirds. It's called sort colors, and I'm going to link it down below if you do want to look at this more in depth. But the way I was taught this was through the use of for loopy questions. Because we are going to be using a while loop to sort through this, we want to keep these 4 questions in mind. Does it start right? Are we initializing our variables correctly for our while loop? Does it stop right? What is our while condition going to be? Does each iteration make progress toward termination? How are we going to increase our pointers to hit that while condition? This is so we don't run into an infinite loop. And finally, does the repetent keep the invariant true? How are we going to maintain the invariant? What is our invariant here? It's just a claim we're going to make. So say over here, right, in this example over here, what I'm going to do is make 3 variables. I'm going to have less than, equal, and greater. And I'm going to have less start at index 0, equal also start at index 0, and greater start at length of nums minus 1. So all the way over here, at the other end of this array. Now I'm going to be making a claim that all the numbers to the left of my less variable over here are going to be less than the pivot. So all the numbers I've seen that are less than our pivot are going to lie to the left of this variable here. Anything between left and equal is going to mark all the numbers that are equal to our pivot. So the difference between these 2 indices is going to mark the number of elements we've come across that are equal to our pivot. Exactly. And everything to the right of greater is going to mark all the elements we've seen that are greater than our pivot. And finally, everything between equal and greater inclusive marks all the numbers we have yet to see. So anything we haven't seen so far is going to lie within these bounds. And this makes sense, right? Right now, we haven't come across any numbers whatsoever. We haven't gone in any while loop yet. So there's nothing to the left of this variable here, less. There's nothing between these 2 indices, 0 minus 0 is 0, so we haven't seen anything equal to our pivot, and nothing to the right of greater. So we haven't seen any number that is greater than it either. And we also know everything within this range of equal to and greater than covers our entire input nums because we haven't traversed anything in our nums just yet. So we know we're starting off correctly. Our initializations are right. Now, based on this, what should our while condition be? We want to make sure we traverse through every single element. So while equal is still less than equal to greater, we're going to keep going in our while loop. So let's go ahead and actually write these down so far. So what we're going to do is have less equal left. Equal is also going to be left, and greater is going to be right. Now, what pivot are we going to pick? It's going to be something random. Let's just say it's the rightmost element in our array. So pivot is also going to be nums of right. And when we first call this function, we're going to call it with our entire input. So we're actually going to be returning quick select with index 0 and length of nums minus 1, which means less is index 0, equal is index 0, greater is going to be index 8, and our pivot is going to be 4. And I'm writing this all in one line just so it's more concise. So we have our initializations. What is our while loop? While equal is less than equal to greater. So we have our while condition done. Now we actually want to compare all the numbers, right? Equal is going to mark all the numbers we haven't seen yet. So we want to see what we have at nums of equal. So if nums of equal is less than our pivot, in this case it is 2 is less than 4, what we're going to do is just swap whatever we have between left and equal and move both down. This is going to become clear once we run through some examples. So nums of equal and nums of less are going to swap. Nums of less and nums of equal. And we want to move both equal and less down. We've seen one number that is less than our pivot, and we said everything to the left of less is going to mark all the numbers we've seen that are less than our pivot. So we move less up by 1, and we also want to move equal down because the difference between left and equal marks all the numbers that are equal to our pivot. So equal also moves up by 1. So less and equal are now over here. And we can actually change this into a while loop. We can keep doing this while we still come across numbers less than our pivot. So let's also change this to be while equal is less than equal to greater, and while nums of equal is less than pivot. So again, we're going to do the same thing. 3 is less than 4. We're going to swap left and equal together and move less up and equal up. Now this while condition is no longer true. Equal is still less than equal to greater, but the nums at equal, so 4 is not less than our pivot. So what do we do if the number we're on equals pivot? So while equal is less than equal to greater, we're just adding this as a safety check so we don't go out of bounds, right, in any of these while loops. So while equal is less than equal to greater, and while nums at equal equals the pivot that we have, all we have to do is move equal up by 1. So equal plus equals 1. This is so we increase that distance between less and equal, because we did say the difference between less and equal marks the number of elements we've seen equal to our pivot. So less is at index 2, equal is at index 3, which means we've seen 2 elements that are less than our pivot, and we've seen 1 element, 3 minus 2, that is exactly equal to our pivot. Now, if we go back in this while loop, we are no longer at nums of equal to our pivot. We are now greater than it. So what do we do in this case? While equal is less than equal to greater, and while nums at equal is greater than the pivot, we're just going to swap what we have between equal and greater. So nums at equal, nums of greater are going to swap. So nums of greater, nums at equal. So 5 and 4 swap, and we can move greater in closer to the middle. We've now seen one element that is greater than the pivot, and everything that is to the right of this variable here marks all the numbers we've seen that are greater than the pivot. So greater minus equals 1, which means we are now at index 3. And we can't also move equal in, right? Because this is now an element that we haven't seen yet. We just switched something unknown to go into equal and took whatever we had at this index that was for sure greater than the pivot into that spot. So we would go back in this while loop over here, equal is still less than equal to greater, and make the same checks again. So while nums of equal is less than pivot, this is not true. What we have here is not less than pivot, so we don't go in this while loop, we go here instead. What we have here is equal to our pivot, so we're just going to move equal down by 1. So equal is at index 4, less is at index 2, and greater than is at index 7. We can't go back in this while loop because we are no longer equal to the pivot. So we go in this while loop. Equal is still less than equal to greater, and nums at this equal over here, which is 6, is greater than the pivot of 4. So we're going to make a swap. We're swapping here and here. So 3 and 6 have swapped, and we move greater in. We can go back in this while loop because nums at equal is no longer greater than the pivot. So we exit, go in this bigger while loop, go in this line over here. Nums at equal is 3. This is less than pivot, so we're going to go in this while condition, and we're going to swap what we have in equal and in less. We came across a number that is less than our pivot, so we want to put it to the left over here, right? So 3 and 4 are going to swap. And now that we have swapped, we're going to move both down. We've seen another element that is less than our pivot, and we still want to maintain that difference we had between equal and less. So we still have those two elements we've seen that are equal to our pivot. Going back in this while loop, we make a check, nums at equal. This is still less than pivot, so we swap again. So 3 would come here and 4 would go here. And we move left and equal down again. We can no longer go in here because nums of equal is not less than our pivot. So we go in this over here. This is true, right? Equal is still less than equal to greater. And nums of equal does equal our pivot. So we move equal up by 1. And now we can no longer go in this while loop, right? This is no longer true. We've covered all the elements we had. And now this is arranged, right? All the numbers that are less than our pivot are to the left of it. Everything equal is over here, and everything greater is to the right. Now that this is done, we want to compare how this relates to the k that we want to return. So if k is greater than this greater over here, that means we know we want to return something that is greater than our pivot. So we're going to call quick select again in this partition. So our left bound is now going to move up, so it's going to be greater plus 1, and right is going to stay as is, and we just want to return the output of that. If that is not the case, so elif k is less than this over here, so less than less, we know we want to look in this half over here. So we are going to return quick select with the left bound unchanged, but we're going to cap it on the right side, right? We're only looking up until this point. So it's going to be less minus 1. And else, if k lies somewhere between less and equal, then we're just going to return whatever we have over there. So we're just going to return nums at greater, for example. Now in our example, k was 4. 4 is not greater than 6, so we don't go in this condition. 4 is also not less than 4, so we don't go in this condition. We're not now going to check between here. So what we're going to do is just return whatever we have at nums of greater, which is 4. So let's go ahead and submit this. Invalid syntax. Oh, we don't need whiles over here, so let's go ahead and fix that. Okay. And there's a typo here as well. Let's fix that. And now if we submit, it is accepted. So this is the solution for kth largest element in an array. We did this in constant space O of 1 and linear time O of n. If you have any questions, let me know down below. If this video was helpful, like, comment, share, and subscribe. It really supports the channel. And as always, I will see you in the next one.